Okay, so this is the outline of chapter 25 about the capacitor. So first we'll introduce the capacitor of capacitance, and then we will also talk about how to calculate the capacitance of different structure. Okay. Of course, the fundamental structure is a parallel plate. Actually, you have seen it in previous chapters. But there are some other shape, some other structure of the capacitors. So we'll talk about how to calculate the capacitance about all these structure. Then we'll talk about the capacitors in parallel and in series. Yeah, maybe you have already learned it before, but yeah, actually it's not that difficult. It's very, it should be very simple. And then we'll talk about the energy stored in an electric field. Energy stored in an electric field. So there are three fundamental circuit elements. So one is the resistor, one is the capacitor, which we'll talk about it in this chapter. For resistor, we'll talk about it in the next, the chapter 26, and we'll talk about the inductor in chapter 30. So for the capacitor and inductor, they will store energy in it. For an ideal element, they will consume and they will store some energy and maybe release it later. So they do not consume energy. They do not consume. They only store some energy in them. In the E field or in the B field for an inductor. Okay, and then. Wow, okay, so and then we'll talk about the capacitor with dielectric. Okay, dielectric 叫做 dielectric 叫做电介质 电介质。Okay, so actually it will influence the so it has a different characteristic with the air. Okay, so there are some interesting property for the dielectric, and it will slightly modify the Gauss law. Okay, so the epsilon naught will turn it into an epsilon. Okay, but yeah, so actually we will slightly modify the Gauss law, but for this course, when we talk about the dielectric, we will not go into deep. Okay, we just try to mention it in a very simple way. And then of course we will talk about the dielectrics and the modification of the Gauss law. Okay, so first, this is the definition of the capacitors. So a capacitor consists of two isolated conductors. Okay, the plates in this example. So in this example here, okay, with charges plus Q and negative Q, okay, its capacitance C is defined from Q equals CV. Q equals CV is very important. Very important for a capacitor. Okay, so yeah. So here we have a parallel plate for the capacitor, and then there may be some charges that are charges onto this plate independently. So maybe this is the cross section. Yeah, this is a 3D plot, and then this is a cross section. So here we have the top plate. We have the top plate. We have the bottom plate. Okay, we have two parallel plate here. 就是两个平衡面或者平衡板。Okay, so so on the top plate we have plus Q charges, and then on the bottom plate we have negative Q charges. So actually there won't be excess charge. So the magnitude on both plates are always equal in magnitude but opposite in sign. So yeah. So they will, the total charge here will cancel out each other. Okay, so actually we have learned it before in chapter 22, chapter 23, and also chapter 24. So actually for this structure, it will generate uniform E field. Okay, at that time we assume this plate is very large, very large, so that it will generate E field on both sides. Or if there is only a single plate with charge plus Q there, and then distribute uniformly, then it will generate E field on both sides. Okay, like this. And if we have a parallel plate, and then we also assume it to be very large. Let's say this is plus Q, this is negative Q. Then it will generate E field in between. Then we will generate uniform E field in between, and there will be zero, E to be zero for the outside part. Roughly like that. And in this case, as much as we have E field, like this, there will be potential, because if you still remember, V equals negative integration of E dot ds, something like that. For this line integral, as long as we have E and also ds, and let's say we have a path. We have a path like this. This is the path we would like to do the line integration. Then we will have E dot ds to be a non-negative value, so that there will be a potential difference. So there will be something like V here and 0 at the other plate. Something like that. Okay, but actually now the plate is not infinitely large, so that it is not actually the same as this case. So in that case, we will assume that between the two plates inside, actually if you do a very precise calculation, it is not that way uniform, but simply speaking, if we just like to use it in our course, we usually will assume the E field between the two plates are uniform. And actually outside there will be something called the fringe E field. Okay, 就是一些边际的一些电场。But actually we will also assume the E field at the outside part will be 0. This is just an approximation. For engineering students, you need to have an idea to try to do some calculation in an approximate way, and then it will make your calculation easier. Although your answer might not be very correct, but it makes you have some numerical idea. 就是在这工程的学生来说的话，就是很多时候我们会对计算做一些近似，这些近似的话，当然会让你的计算没那么准确，可能有一些误差的出现。但是有这些近似之后，你就能够算得起来，因为有时候工程来说，有很多东西都会有误差，所以有时候你真的算得那么准没有必要。但是对于你来说，你近似完之后，你可能很快可以得到一个数值的一个感觉，其实是更为重要。Okay, so here it says a parallel plate capacitor made up of two plates of area A separated by a distance d. Okay, so the cross-section area, the area of a plate is capital A, and then there is a small distance d between them. There is a small distance d between them. So the charges on the facing plate surface have the same magnitude q but opposite side. Okay, just as what I mentioned. Here it says, as the field line shows, the electric field due to the charged plate is uniform in the central region between the plate, although it is not that uniform, but we'll try to make this assumption. The field is not uniform at the edge of the plate. as indicated by the fringing of the field lines there. OK， 就是有些边际的电场在外面。Okay, so here we have a practical device here to form a simple circuit. So here for this part is the capacitor. Okay, so we have two square plate placing close together, and then here we have a battery. We have a switch 就是有个开关，有个电池，有个电容把它串在一起。Okay, so yeah, so of course if you need to draw it every time, then it will be time consuming. So we have some circuit symbol so that we can use some simple line art drawing to actually show what is your circuit. So here for the battery, we try to draw two lines. One longer, one shorter for the battery. Okay, and then the longer line means this is the positive side, or this is the negative side. Okay. Sometimes in our circuit theory, I will try to use another symbol, something like this. Okay, this is actually the same thing. Okay, something like this. Okay, yeah. I just try to try to write it like this, and then it means this is a voltage source. Voltage source 就是电压源。Okay, so in that case, I will simply draw it like this. Okay, then it is done. Okay, this is a C, this is a switch. Okay. Okay, for the capacitor, okay, we also use two parallel line to specify this is a capacitor. Yeah, but these two, the only difference is that these two lines is one is longer, one is shorter, and then for the capacitor, both lines are with equal length. Okay, so you must draw it carefully. Otherwise, if you try to draw it not so elegant, then you may mess up with it. Okay, so that's why sometimes I will use this one. Okay, this one, even you don't draw it very elegant, then you still can distinguish. But sometimes whether it is equal with an equal length, then it is not easy to distinguish sometimes. Okay, and then for this one is a switch. Okay, so this is the open state, and so if you just connect here, then it is just like a perfect wire. Okay, so this is a switch. Okay, for the bottom part, it just said if at the beginning this switch is open, open 就是 open. So in English we will call it open and close. Okay, open and close. So so we must be careful because in Chinese 我们会说开跟关，但是这个是开路这个是闭路。开路是这个状态闭路的话是这样，就是导通的。那跟你中文的关是相反的，所以要注意。有时候英文的话，它会说 open and close，open and close。open 就是开，就是断开，这个开是断开的意思。close 的话是接上。那如果你真的要讲中文的开关的话，是 switch on switch off，switch on switch off。对。Okay, so here it just said at the beginning the switch is open so that this battery is not fully connected with this capacitor, so there is no charge on it, and if this charge is closed, then this battery is directly connected to this capacitor, so that they will charge some. So in that case, it will be something like we have a battery and then this capacitor, and then this switch is closed. Although for a circuit symbol, we seldomly try to draw it like this. I just try to let you have idea of. For this case, the switch is closed. This switch is closed. Okay, in that case, we have a battery here with a potential difference. So in that case, there will be positive charge on the left plate and then a negative charge on the right plate. Okay, something like this. And there will be potential difference, something like V plus minus, something like this. Something like this. 这个是正极的话，就是 charge 到这边的话，这是正电荷；这边负极的话，传到这边它就会负电，是这样。Okay, so by any questions? No? Okay, so here we try to talk about how to calculate the capacitance for the parallel plate capacitor. So actually we'll make use of Gauss law. We'll make use of Gauss law. So here we have two parallel plate here with some thickness for the plate, and here we suppose we have some battery outside. Okay, so let's say something like this. We have a battery here, okay, to provide a potential difference like this, okay, with a potential difference V. So in that case, this is a positive side, okay, there is some positive charge on the top plate and then there's some negative charge on the bottom plate, okay, so the magnitude of the charge will be the same but opposite side, so plus Q here, okay, plus Q here, negative Q here. Okay, so here we try to apply the Gauss law for this one, okay. This red dotted box, okay, is the Gaussian surface. It's a Gaussian surface. Of course, it's 3D. Okay, it is 3D, but yeah. So there'll be something like this. This is one phase. This is the second phase, the fourth phase, the third phase, the fourth phase, and then of course there are some phase here, and then just at the back of the board. Okay, but those two phases won't contribute because you can clearly see that for the phase here, it will be all the way perpendicular to the E field, so it won't contribute E dot dA. The E dot dA won't contribute anything. Okay, so here we just need to consider this this 1, 2, 3, 4 surface, and clearly this one and this one won't contribute anything either. Yeah, because the dA just point to the left and right side, so it is perpendicular to the E field, or actually it's just outside the capacitor, so there won't be any E field there. So what we only need to consider is the top surface for this Gaussian surface. Yeah, so this is the first one, and then this is the second one. And for the top one, actually this one is inside the conductor. And as I have mentioned previously, inside the conductor there won't be any E field. Okay, so for this surface, for the top surface of this Gaussian surface, it won't contribute to the E dot dA either. Okay, so the only surface that will contribute to the Gauss law is this one. Okay, so here first we try to write out the Gauss law, epsilon naught times E dot dA for this Gaussian surface equals Q enclosed. Q enclosed in this case is positive Q here. Okay, so for this Gaussian surface is only enclosed. Only the plus Q charge is enclosed. This negative Q is outside. Okay, so this is the very first equation, and then yeah, we actually use the potential, the definition of the potential in chapter 24. So Vf minus Vi equals negative of integration of E dot ds from I to F. Okay, so here how do we define the I to F path? So actually this is the I, this is the F. Actually, it is pointing upward. Okay, and as we know, the E field will be pointing downward. Yeah, it should be starting from the positive charges to the negative charges. So, yeah, based on plus Q on the top and then negative Q on the at the bottom. We already know that the E field should be uniform and also pointing downward, all the way inside this region. Okay, but here we try to define the I point at the negative plane and then the F point, the final point at the top plate. Okay, because yeah, it turns out to be a positive potential difference. Okay, so we will have something like, oh, this is V. Sorry. This plate will have VF. This plate will have VI. Oh, so it will be a 0, and then it turns out to be a normal V. So the potential difference will be a positive V. So we define the path like this. Okay, so in that case, the ds is pointing upward. Okay, the ds is pointing upward, and then the E field pointing downward. So E dot ds will be negative. E dot ds will be negative E times ds. Okay, they point to opposite side. Cosine of 180 degrees, -1. So it is negative E times ds. So this negative sign will cancel with this one. Okay, so on two negative sign turns out to be a positive sign. So it becomes something like this. Okay, Vf is V, Vi is 0. So this is V, and then two negative sign become positive. So for the I, for the negative, for the I point, it is a negative plate, and then for the F point is the positive plate, and then this dot product already becomes a multiplication E times ds. Okay, so it becomes something like this. Okay, so next, yeah, here we see it here. So we assume that the plate of our parallel plate capacitor are so large and close together, and that we can neglect the fringe. Okay, so it is some sort of approximation. Okay, to neglect the fringe E field outside the capacitor. Okay, and taking the E to be constant throughout the region between the plate. This is the second approximation. So 就是有两个近似，一个就是假设外面的 fringe 都小到忽略不计，然后另外一个的话就是两个平衡板中间我都假设它是它都是均匀的。其实实际上的话，就是在接近边缘的地方的话，它会弱一些些。就是比如说在这里，跟在这里的话会稍微弱一点，但是简单算的话，我们就做这个假设。Okay, so here we draw a Gaussian surface that encloses just the Q. So this is what I mentioned. So in that case, just now it is still epsilon naught times integration of E dot ds and E dot dA. So as I have mentioned, all the other 5 phases won't contribute to the Gauss law. Only this part will contribute to the Gauss law. And for this surface, dA is pointing downward. Okay, so dA has the same direction as the E field. So E dot dA becomes E times dA here. Okay, and actually E is a constant, so integration of E times dA becomes E times A. Okay, becomes E times A, something like this. Okay, so this thing becomes this thing. Okay, so it turns out to be epsilon naught times E times A equals Q. Okay, so yeah, so in the previous page we have this equation, and also E is a constant, so we can just put this E out, put this E outside. So this is just integration of ds. So which means it is just the length of this path. The length of this path is the distance d between these two plates. Okay, so this integration of ds from negative to positive becomes simple d. Okay, so this one becomes the d. So here quickly we have v equals e times d, and also we have this equation. So we try to eliminate e. We try to eliminate e, which means we have based on this equation, we have e equals v over d. Okay, we just divide d for the whole equation, so we have e equals v over d like this, and then we try to plug this equation into there. So we have epsilon naught e equals v over d here, and then a equals q, and then we also use the definition of the capacitor q equals cv. Q equals cv. So we have this cv here, cv here. Okay, so finally we can simply cancel this v and this v. This v doesn't matter. So finally it becomes c equals epsilon naught a over d, a over d. Okay, so this is very important. This is very important. So the capacitance for the parallel plate capacitor so equals this epsilon naught is a constant 8.85 times 10 to negative 12, and then this is the area of a plate, area of the plate. This is the distance between the two plates. So if you would like to have a larger capacitor, then you can either increase the area of the plate, or you try to decrease the distance between the two plates. Okay, so this equation is for the parallel plate capacitor. Okay, so for the next case is the cylindrical capacitor 就是一个圆柱形的电容，对，那一般的话就是会讲这个 parallel plate capacitor 介绍为电容，但是 cylindrical capacitor 其实是很常见的，就是如果你有兴趣去怎么说，自己去拼电脑的话，你打开它的话，那个主机板上面有很多那种圆柱形的那个，它那些就是电容它那些是电容，一些电解电容它会有一个比较大的电容值，但是如果你接错方向的话，它会爆炸的，它会爆炸的。它爆炸的话是有一些肉松的香味的。以前，因为我以前电子实验的话，就是有时候助教就会说，你可以接这个电容上去，让你的电源稳定一些。那然后，但是你要注意啊，就是它就会有一个像圆柱形的然后有一只角长一些，有一些短一些。那长的那一个就是正极，短的那个负极。那然后你说他就说你要接对方向，接反了它会爆炸。那然后你接了之后有时候你电路不稳定，有时候你测不出来，你接上去之后你的电源就会稳定一些。但是有时候就是因为通常你拿那些 这些元件通常是一个实验室里面一个大的抽屉里面你拿一个出来用，用完之后放回去。那有些人就会长一只长一只短嘛，他就会把长的跟剪短剪成短的放回去，你用的时候你又反过来，所以有时候就会看到做一做实验，听到啪一声，就是好像你拿着几本书放在腰那么高的高度，然后放啪一声，大概是那个爆炸的声音，就它不会很强，就是大概几本书掉在地上的那种感觉，然后就会闻到一些肉松的香味，就是那个电解电容。Okay, so let's come back. So we talk about the mathematics about this cylindrical capacitor. So here we only show the cross section. We only show the cross section. Actually, if I like to draw it in 3D, it would be something like this. 那就是有一个圆柱形，它会有接两根角出来的。那这个是横切面，就是你把它对着这个圆柱的那个圆的那个面切开的话，它就是有一个内的那个小的同心圆，有一个外壳。那两个外壳的话，它就是一个弯曲的平行面它就是弯曲的平行面。这两个同心圆的话，它们就是平行。它虽然不是平面，但是它们平行的嘛。它们就是每个地方，它们都有一个最短的那个距离，都是一样的。Okay, so in the cross section, a cylindrical capacitance of length L. Okay, so for the length, it is talking about this one. This is the length L, formed by two coaxial cylinder. Coaxial 就是同轴的意思这个是同轴。同轴的话，因为它是，如果它是圆的话，我们叫同心嘛。那它是圆柱体的话，就是同轴。同轴的话，就是每个圆的圆心，就是每个平面的圆心，把它连起来的话，它就是一个轴嘛。那两个圆柱形的轴同一根，它就叫同轴。Coaxial cylinders of radii A and B. Radii 就是 radius 的复数嘛 ，radius 的复数 ，radii A and B. Okay, so the smaller one is A, and then the larger one is B. Okay, so here we assume that this L, the length is much larger than the radius, the outer radius, the outer radius, so that we can neglect the fringe of the electric field that occurs at the end of the cylinders, at the end of the cylinders. 所以的话，就是它虽然不是无限长，但是至少有一些假设，就是说这个 L 这个长度的话，还是要比它们的半径来得大，或者是说类似的。就是比如说这个面是 A 这个 A 这个面积，或者是它的长度可能是开根号 A， 那这个开根号 A 也要远大于这个 D， 你做这个假设才会比较近似不然的话它的误差就会偏大一些那这个也是类似就是 L 要远大于 B， 那这个假设才会比较接近Okay, so each plate contains a charge of magnitude Q. Here, charge and field magnitude E is related as follows. Okay, so here we have this equation. Of course, at the beginning, we can always try to write out the Gauss law. Epsilon naught integration of E dot dA equals Q enclosed. Okay, so here, what we are trying to do is we have some negative charge outside and then we have some positive charge inside. Okay, and then here the Gaussian surface. Where is the Gaussian surface? This one is the Gaussian surface. The red circle is the Gaussian surface, or the red cylinder. Okay, you also try to define the Gaussian surface is a cylinder. 就是还是一个圆柱形，只是在这个横切面上面 你就只看到一个圆形。那当然上面那个圆形跟下面那个圆形的话，也不会贡献这个 E 到 dA， 因为那两个面的话，一个指着你自己的方向，一个指向纸的方向，所以也会跟这个 E field 会垂直，因为这些所有的 E field 都是镜向的，就半径的方向的，所以它都不会它只会对于侧面会贡献。Okay, so in that way, so for example, for the Gaussian surface at this point, okay, at this point, the dA is pointing like this, okay, like this direction, and then for this point, dA is pointing to this direction. So it will be all the way point to the same direction as the E field. So in that case, this E dot dA turns out to be a multiplication, E times dA, and E field for a specific radius, R. Okay, so this is a R, this is R. For when you try to fix the R, the E field will be the same because so because these two cylinders are coaxial. These two cylinders are coaxial. So if you just pick a Gaussian surface which are also coaxial and then with a fixed radius, then it is all the way symmetric. Okay, so throughout this Gaussian surface, the E field will be constant. So in that case, we will try to put this E outside. Okay, so it turns out to be the surface integral of the dA, which means the area of this cylinder, actually the side here. Okay, we just don't consider the top and the bottom. Okay, we only consider the surface of the side. So for the surface of the side, we try to cut it out. And then we try to flatten it, and then it become a rectangle. So the height will be L. And then the width will be 2 pi r. Will be the 2 pi r. We just try to cut it like this and then try to expand it. So this is the width. This is the width of this rectangle. So 2 pi r times L will be the A equals 2 pi r times L will be the area. So we just put 2 pi RL here. This is the EA. Okay, EA, this is the A, this is E, this is epsilon naught. Okay, so this is this side of the Gaussian surface, and then for this Gaussian surface only enclose the positive Q. The negative Q is outside, so here is positive Q. Okay, so here we can have the expression of E. So we just keep E on the right side and then move all the variable to the left side. So we have Q over 2 pi epsilon naught and then RL, 2 pi epsilon naught RL. Q and then 2 pi epsilon naught and then R here, L here. Okay. For this ds, we start from the negative plate. Start from the negative plate to the positive plate. Okay, so this is the ds direction. Okay, but for the cylindrical coordinate, 就是圆柱坐标系的话，它会从中间开始算啊，这边是 R 的方向，这边是 R 的方向。Okay, so in that case, if you try to change ds into dr, okay, because it is something like R points to the opposite side to the s direction. So in that case, dr equals negative ds. R equals negative ds. So in such a way, ds, if we change it to tr, we have this negative side here. Okay, so in that case, r is this integration variable. So r, we put r inside this integration sign and then all the other variables, put it in the front. Okay, so in that case, dr, we try to integrate from B to A. B is the negative plate, okay, referring to the radius B, okay, although it's larger. And then A is the smallest one, okay, smaller one. So this is A here. Okay, so if we just put this negative sign inside the integral, then we will swap the lower and upper bound for this definite integral. So it turns out to be q over 2 pi epsilon naught L integration of dr over r from A to B, Okay, so this negative sign will just swap this A and B. Okay, if you try to integrate this 1 over r, this is just the lateral log. Lateral log, okay, so lateral log of r, and then you vary from A to B, so it will be lateral log of B minus lateral log of A. So it will be lateral log of B over A. Okay, so finally, if we look at the leftmost and the rightmost part, this is the expression of V. But what we would like to find is the capacitance. The capacitance is actually Q over V. Okay, so the V is here, the Q is here. The Q is here. So we can actually put V on the right side. So we have Q over V, and then put all the remaining variable to the other side. So it turns out to be 2 pi epsilon naught L going to the numerator, natural log of B over A going to the denominator. So this is the expression of C for this cylindrical capacitor. Okay, so